Welcome to massive open online course on chemical process intensification. So, we are discussing in the module 8 regarding interfacial area based process intensification. In the previous lecture, we have discussed something about the different configurations of the ejector systems and their applications, and also how that ejectors is working for the generation of micron size bubble, as well as the droplet for that creation of the interfacial area for the mass transfer in chemical engineering processes. So, in this lecture we will discuss something more about that ejector system and how that ejector system is working in the downflow system and what are their different hydrodynamic characteristics that we will discuss in this lecture. So, this lecture will be included the subject on hydrodynamics and transport in downflow systems, and in that case we have discussed something about what are the functions of that downflow systems that working in a particular chemical engineering processes for their intensification. So, as per the downflow system, it is generally considered a units for carrying out the reactions and mass transfer operations, in which a gas that will be made up of one or several reactive components that comes into a contact or reacts with a liquid. That liquid may be in continuous or base wise in mode. In that case, they are characterized by the fact that the gas is dispersed in the continuous liquid phase in the form of dispersed phase of bubbles against its buoyancy, which will be that creating more interfacial area as well as residence time in the liquid medium, and during that formation of the bubbles, it will be flowing downward due to the liquid movement. And these things already been described in details in the previous lecture. So, we will discuss that what are that actually ejector system, how it is being used for that downflow system. In that case, this ejector system will suck the gas from the atmosphere or from any other sources by sucking it by the liquid jet, and then it is pumping into the pool of the liquid. And in that case, the breaking of the surface of the pool of liquid and entrapping the gas into the liquid as a bubble, and in that case the dragging downward by the downward liquid momentum will be the more important phenomena, where that you can get more residence time in that particular downflow system. And also we have discussed that the motive fluid, whenever it will be expanded through a usually converging diverging section of that ejector, sometimes that nozzle will be giving you the high velocity, and because of which there will be a high kinetic energy and formation of the low pressure somewhere as per that Bernoulli's equation, and then the high velocity and the low pressure will be used to entrain the suction fluid through the the suction nozzle, and the motive and suction fluids are then mixed in the mixing section. And also this high speed mixed flow is then decelerated in the diffuser, and static pressure where it will be recovered, and then it will result in a pressure that will increase to the suction stream across the ejector, and then exponentially whenever it will be increasing interest in the ejector technology that can be utilized for that particular chemical engineering process for the intensification, and it is happening since 1995 as a key word of that ejector system and its application. So, this is basically achieved by the mechanical co-location of the gas phase in flow to the point where a maximum shear of the motive liquid occurs, and in that case highly momentum that forces will be actually used to recommend for the following types of reactions, like that amination, alkylation, ethoxylation, hydrogenation, carbonization, nitration, oxidation, etc. There are several other applications in the chemical engineering process based on these ejector systems, where that generation of the interfacial area just by dispersing the liquid opposite to its buoyancy force in the case of downflow system. And also we have discussed the different configurations like upflow, downflow and horizontal, that is in details in previous lectures we have described. Now we will discuss that hydrodynamics in that downflow system, where the ejector is being used for the entraining gas in the column. See this setup here in the slides, that how this liquid is coming inside through the jet, and whenever jet is coming to the column, it will suck the gas from this location, and then it will be dispersed in the liquid by entraining that gas as a dispersed phase of bubbles. And due to this downward movement of the liquid through the column, and then it will come to the separator, and in the separator it will be separated, and it will be coming out from the outlet of this system here. So in this case, what are the different hydrodynamic characteristics whenever this downflow of the liquid, whenever it will be entraining that gas as it is dispersed phase of bubbles, and in that case what are the different mechanism and what are the different hydrodynamic characteristics. The mechanism we have already discussed, but what is the hydrodynamic and transport characteristics for these systems. Now in this case you have to know that what will be the hold up characteristics, gas hold up characteristics, and also now how to analyze that hold up characteristics in the downflow system, and also what are the different friction or pressure drop and how to analyze it, bubble size distribution or drop size distribution, and how to measure this drop size or bubble size in this particular system, and what is the interfacial area, how to estimate those interfacial area that is created by generating that bubbles or droplets in this particular downflow systems by ejector system. And also mixing is the one important factor in this case, whenever jet will be plunging into the pool of the liquid and forms the bubbles and dragging it downward against its buoyancy. In that case you will see there will be intense mixing of that gas liquid in a mixing zone. So in that case you have to know what is the degree of mixing or what extent of mixing happening inside the column whenever jet will be plunging this gases or entrapping that gases or entrainment of that gases into the column. And based on that what should be the mass transfer and heat transfer characteristics, that also to be known. So these are the different hydrodynamic and transport phenomena of this this downflow system for the process intensification. Now since this volume fraction or hold up of the phase is one of the important hydrodynamic characteristics there, because it governs the mass transfer phenomena and heat transfer phenomena. If you increase the hold up or volume fraction of the particular phases in that systems, you will see there will be increase of interfacial area, because if you increase the gas hold up, suppose gas liquid mixture in the downflow system, then in this case this interfacial area, specific interfacial area directly related to that gas hold up. And also if you have that size of that gas bubbles, then you can say what will be the amount of that interfacial area based on that size of that bubbles. So this gas hold up and size of the bubbles are those most important factors for the creation of the bubble and also the interfacial area there. So in this case you have to know what actually how this gas hold up will be defined and how it can be measured. So this volume fraction of the dispersed phase, it is called hold up, generally it is called hold up. Now if it is a particular gas phase volume fraction, then it will be called as gas hold up. So this gas hold up will be defined as this volume of that gas divided by the total volume of gas and liquid. So in general it can be defined as that if suppose there is a mixture of discrete phase and continuous phase, then you can consider that discrete phase as D and continuous phase as that C. So in that case if we consider that volume of the discrete phase in that case you can say that those phase will be dispersed in the continuous phase, that will be discrete phase. So, this discrete phase, volume of the discrete phase out of the total volume of discrete and continuous phase, those fraction will be considered as a volume fraction of the dispersed phase or discrete phase. So, this is generally denoted by alpha, and d here in this case it is denoted for that dispersed phase. So, alpha d will be equal to V d by V t. What is that V d? V d is the volume of the dispersed phase and t is the total volume of the dispersed phase and continuous phase. It can be defined either way, like here this cross sectional area of the dispersed phase that is occupied in the system or in a particular vessel or in a conduit, you can say, and out of total cross sectional area. So, this volume fraction of the dispersed phase can also be defined by this equation here, like AD divided by A. AD is the cross sectional area of dispersed phase, and capital A, that is the total cross sectional area of the vessel or that conduit in which this gas and liquid mixture will be there. And the volume fraction of the continuous phase, of course, will be, if it is binary system, that the remaining portion will be the that volume fraction of the continuous phase. So, that volume fraction of the continuous phase can be defined as the volume of that continuous phase out of total volume of discrete and continuous phase. So, it will be defined as alpha c is equal to V c by V t, where V c is the volume of continuous phase and V t is the total volume of the continuous and discrete phase. It is also defined as like this AC by A. AC is called that cross sectional area of the continuous phase, and A is called the total cross sectional area of the gas and liquid phase, where it will be flowing in a continuous phase. So, in this case V d is the volume of the dispersed phase and V c is the volume of the continuous phase in the total volume of V d and V c. So, in this case volume fraction of the dispersed is often referred to as the hold up. So, you have to remember that hold up means volume fraction of the particular phases. So, either it may be that continuous or dispersed phase. Now, for the gas liquid two phase flow, the gas is dispersed and liquid is continuous. In that case, this gas hold up will be defined as that alpha g. This is alpha g, that means here gas hold up for the gas here. So, alpha g for here gas. So, it will be simply volume of gas out of volume of gas plus volume of liquid. So, it will be like this Vg divided by Vg plus Vl. V is the volume here, and liquid hold up will be equal to alpha L, that will be equal to volume of liquid by volume of gas plus volume of liquid. Here it will be defined like this. But these two phase, whenever we are considering that binary phase, then alpha g and alpha L. So, in that case the summation of this alpha g and alpha L will be equals to 1 for the binary system. Whereas, if you are considering that the three phase system of gas, liquid and solid. So, in that case what will be the volume fraction of the gas out of total volume, what will be the volume fraction of liquid out of total volume, what will be the volume fraction of solid out of total volume. So, in that case you can get separately that alpha g, alpha L and alpha S. Alpha S is the volume fraction of the solid. So, alpha g plus alpha L plus alpha S, that will be equal to 1. So, that is for three phase system. So, here in this case if you consider this this figure, if you consider that is a one column where you can consider it that counter current operation or co-current operation. If you consider that co-current operation, from the bottom gas will be flowing and liquid also will be flowing. So, in that case the gas will be coming out at this outlet and liquid will be that inlet outlet from this location. So, this will be a co-current upflow, whereas the downflow system where liquid will be coming out from the top and gas is also coming in from the top. So, that will be co-current from the top to bottom. So, this is called downward movement of the gas flow and liquid flow. So, this is called downflow system. So, in this case how you will measure that gas hold up? Very interesting that if you suddenly stop that operation. Okay, let us consider this first. Here suppose without any operation, without any the gas or liquid flow rate, what will happen in the column? If you consider this is the column, and in the column if you consider that initially the liquid phase, initially liquid phase will be a certain height like this. So, this is your initial liquid phase. Okay, now if you allow that liquid jet to be plunged on this pool of the liquid, you will see the gas will be entrained, and accordingly you will see after entraining that gas, the mixture of this gas liquid volume will increase and it will go up to a certain level. So, this is up to this, it is called mixture volume. So, this mixture volume it will come at a certain gas and liquid operation velocity or operational flow rate. So, in that case you will see at a particular z velocity here, in this case you will see that gas liquid mixture will be coming up to a certain height of this column. Now, if you at that particular condition, if you take this measurement of height, then if you can calculate what will be the volume of that gas liquid mixture, that easily you can calculate what should be the cross sectional area of the column and what will be the height of this here, height of this gas liquid mixture, then you can easily calculate what will be the volume of this gas liquid mixture. This is simple, A into suppose the gas liquid mixture height is AC, then you can calculate what will be A into AC, that will be your total volume of gas liquid mixture. Now, very interesting that if you suddenly stop your operation of this liquid, what will happen? You will see this gas liquid mixture height gradually decrease and it will come to a certain height where you can get the only clear liquid height. That means that after a certain time all the gas which was entrained into the liquid by the liquid Z, it will be degassing or disengagement of the gases, and gradually whenever disengagement will happen, the gradually that liquid level it will come down to a certain height here. So, this will be your clear liquid height, there will be no entrained of the gas into the liquid. So, that will be clear liquid height. So, we now know that at a particular operating condition we are getting the total gas liquid height, and after a certain time after stopping that operation you can get the clear liquid height. Now, at this clear liquid height what will be the volume of that liquid that is inside the column, that you can calculate easily what will be the cross section, that is A into height of this clear liquid height, let it be here Si. So, this clear liquid height and this clear liquid volume if you calculate and if you subtract from this total volume of this gas liquid mixture volume, then you can easily obtain the how much volume of that gas is entrained into the liquid. So, that entrained gas volume will be called as volume of the gas that has been entrained. Now, this gas volume fraction, that the volume fraction of this volume can be calculated by this volume of this gas divided by total volume of gas liquid mixture volume. So, that is why we can have this is your volume of gas entrained and this is your volume of gas entrained plus volume of liquid here. So, this will be your total gas liquid volume and this is your what is this? This is the volume of gas entrained. Now, this can be calculated, this volume of gas can be calculated, this total gas liquid volume mixture minus what will be that clear liquid volume mixture, and out of this you can calculate this total volume of gas liquid mixture here. So, from this that division of this gas liquid from this gas liquid mixture what will be the gas volume, that you can calculate A into C minus A into H I, then if you divide it by the total volume fraction, then you can obtain that gas volume fraction there. So, it can be easily calculated as that if you cancel it A, then you can simplify it by this 1 minus Si by Lc or Hc here. Hc means total gas liquid height here Hc. So, here you can calculate the gas hold up in this downflow system, it is simply 1 minus Si by Hc. What is Hc? Hc is the gas liquid mixture height during the operation at that particular condition, and what will be the Si? Si is the initial or after degassing the all gases what will be the clear liquid height. So, from this calculation you can easily measure what will be the volume fraction, but this volume fraction of the gas will be overall gas volume fraction. It will not give you that locational gas volume fraction, or you can say that axial gas volume fraction you cannot get here. It is simply that overall gas volume fraction. And also you will not get this radial gas hold up. This gas hold up may be that changing with that radial position, but if your column is very narrow, if it is less than 5 centimeter, you can expect that radial gas hold up distribution will be that negligible, and in that case only overall gas hold up will be the enough to consider there. Now, how to analyze this gas hold up? Whenever you are measuring this gas hold up, you will see there will be a different effect of parameters on this, effect of variables on this gas hold up. Maybe this gas hold up will be changing with respect to that nozzle diameter. This gas hold up will be changing with respect to physical properties of the system. You can say that this gas hold up will be depending on the how this entrainment is happened, and this entrainment, what will be the minimum entrainment velocity, and what will be the minimum entrainment velocity beyond which that you can expect that gas hold up. This is the things, and after getting that overall gas hold up, you can analyze that gas hold up to predict based on that experimental data by a certain model. So, there are two actually models are available to analyze this gas hold up data, that is called sleep velocity model, another is called reflux model. And also since this gas hold up depending on different variables, maybe that more than 2, 3, even 5 also, there are several variables at a time that will be affecting on that gas hold up. So, in that case this complex that dependency of these variables on this gas hold up effect, then you can actually predict this gas hold up based on these different variables just by making a general empirical correlations. So, we can analyze this gas hold up, first of all this sleep velocity model, then reflux model we will discuss also. Now, as per sleep velocity model, you can say that the sleep velocity of the bubbles that will be relative to the surrounding liquid, that is defined as, that is how that is sleep is happening, means what that whenever gas is flowing against the buoyancy, even that along with that liquid, you will see that there will be a sleep between that gas and liquid. Now, if gas and liquid both have the same velocity, then there will be a sleep velocity, it will be that 0, but if there is that opposite of that gas and liquid velocity, in that case you can get that more sleep, that means there will be certain sleep that you can obtain by that subtracting or adding that gas and liquid velocity. So, Vs will be defined like this, Vs will be equal to plus minus Vg minus Vl, and what is that Vg? Vg is the actual velocity of the gas and Vl is called actual liquid velocity, whereas this actual gas velocity will be defined as that Vsg by epsilon g or alpha g, you can say. Vsg is called superficial gas velocity and epsilon g is called that gas hold up in that gas liquid mixture. So, this will give you that actual velocity. This actual velocity is greater than the superficial gas velocity, and actual liquid velocity will be equal to Vsl divided by epsilon L, that epsilon is nothing but 1 minus epsilon g. So, if you know that gas hold up, then you can easily calculate what should be the that actual velocity of the gas and liquid. If you know the actual gas velocity of that gas and liquid, then you can easily calculate what should be the sleep velocity. For the downflow system, you have to consider that this negative sign, and for that upflow system that will be positive sign here. So, to account the interaction between bubbles with the column, the following relationship can be obtained as here given. So, Vs will be a function of that gas hold up, that is sleep velocity will be a function of gas hold up, because this sleep velocity is actually the relative velocity of the actual gas and liquid velocity, those who are related to the gas hold up. So, sleep velocity can be related by this equation. where in this case one parameter it is called Vb. This Vb is called bubble rise velocity, and function of epsilon g, f epsilon g will give you that certain function of the gas hold up in that particular system. So, this Vb will give you the bubble rise velocity, and if you know the bubble rise velocity, from this sleep velocity you can calculate what will be the function of that gas hold up there. Either way, if you know the that sleep velocity from that experiment, actual velocity of gas and liquid, and if you can calculate the sleep velocity, then you can directly relate with that certain gas hold up function. So, that gas hold up function may be either in a straight line form or some other that nonlinear equation may be there. So, there are several functions will be there for that function of the gas hold up. For the special case of downflow system, you will see that this sleep velocity will be a function of gas hold up like this. Here it is given that Vs will be equal to lambda into epsilon g to the power alpha and dr to the power beta, where dr is called that ratio of nozzle diameter to the column diameter, and in this case Vb will be defined as lambda into dr to the power beta. Here lambda is one parameter which will be obtained from the experimental data. So, in this case downflow case, this Vb can be obtained within this range of velocity of 0.73 to 1.80, that is meter per second, where alpha is the coefficient that will be 3.05 and beta will be equal to 0.58, whereas lambda, that is parameter, will be equal to 4.51. So, for this downflow system you can obtain this sleep velocity based on this equation. Once you know this sleep velocity, then what would be the epsilon g, you can easily calculate that epsilon g. And other way, that upflow system you can compare with this downflow system, then you will see that this Vs will be equal to Vb into 1 minus epsilon g to the power m to the power n, where for the upflow system you will see that Vb will be equal to 0.79, m is equal to 1.0 and n is equal to minus 1. And for again upflow system, another correlation it is developed based on that Harrison experimental data. Then they got that this Vb will be equal to 1.0 and m will be equal to 1.0 and n is equal to minus 1. Whereas, in case of bubbly downflow, this Vb should be equal to 0.03 and m is equal to 1 by 3, n is equal to 1.0 and m is equal to 1, n is equal to minus 2.28 as per Jardanic et al. 1997. So, here in this case, this is actually depending on the that how you are defining that gas hold up function. So, in case of Majumdar et al. That is published in that 2006, that here in this case you will see that as per this function this Vb should be within this range, where alpha beta will be defined like this. But in case of Jardanic case, they obtain they have actually suggested this function of this sleep velocity like this, and according to their model this Vb will be like this, it is given here 0.03 where m and n are 1 by 3 and 1.0 respectively there for the downflow system. So, we can get that upflow and downflow system in the separate way for analyzing that that what should be the bubble rise velocity in the downflow system and what would be the upflow system based on this sleep velocity model. Another model, it is very important to analyze that gas hold up, how to predict that gas hold up based on this model. It is called the drift flux model. In this case, you will see whenever gas will be flowing as it is first phase of bubbles, you will see that the one gas bubbles will sometimes push another bubbles, maybe the surrounding gas bubbles also will be drifted by the bottom bubbles or surrounding bubbles. So, in this way one bubbles will interact with the other bubbles. So, whenever they will be moving, the that near bubbles will push another near bubbles to that that moving up, even going downward. So, there will be interaction and there will be pushing, or you can say drift the one bubble by the another bubble. So, this is called drift velocity will obtain by another bubbles. So, in that case what will be the normal rise velocity of the bubbles, that will be enhanced by the drift of another bubbles. This happened for the droplet also. So, based on that droplet or interaction of the bubbles, what will be the change of bubble velocity and what will be the flux of that velocity change. Joubert and Freundlich 1965 they have developed this model to analyze that gas hold up based on that interaction of the gas bubbles and also the drift, that means relative velocity of the gas bubbles whenever it will be flowing in a certain reactor of gas liquid system. So, in that case Vg will be actually considered as the actual gas rise velocity, and it will be defined as Vsg by epsilon g. What is that Vsg? V is the superficial gas velocity and epsilon g is the gas hold up in that particular system. So, it will be a function of gas liquid mixture velocity, and according to that model this function may be that linear function and may be non-linear function. So, according to that Joubert and Freundlich, and considering that interaction of the gas bubbles and also velocity distribution of the gas inside the reactor, they suggested that this actual velocity of the gas will be as a function of mixture velocity and it will be a linear function. So, based on that linear function they have defined that this Vg will be is equal to what, that it will be C0 into Vm plus Vd. This Vd will be representing that weighted average drift velocity of that discrete phases, which will accounts for the effect of local relative velocity of the gas bubbles there. And this C0 is the coefficient of that reflux model. This C0 is the distribution parameter which accounts for the effect of non-uniform flow. If there is a non-uniform flow, you will see there will be interaction of the bubbles will increase. That means here radial directions, axial direction, random motion of the bubbles and interaction of the bubbles will be increased. So, it will actually give you the degree of that interactions based on that distribution of the velocity, whether it will be uniform velocity or non-uniform. Generally for uniform velocity you will see the interaction of the bubbles will be very less. So, in that case you will see that drift velocity will be relatively lower than that non-uniform flow case. So, C0 is the distribution parameter and it will account the effect of non-uniform flow. Now, how will you estimate that C0 and Vd? What will be the value for that? It may be for upflow system, it may be for downflow system, that will be different, and of course, it will give you that uniformity, non-uniformity, degree of uniformity, non-uniformity and also the drift parameters or drift velocity in the system. So, it can be obtained from the experimental data. First of all, you have to do the experiment for the estimation of gas hold up. Once you know the gas hold up, you can have the actual velocity of the gas velocity there. So, if you know that gas hold up, then what will be the superficial gas velocity, that can be calculated from your gas flow rate divided by the cross sectional area. So, once you know that superficial gas velocity and gas hold up, you can easily calculate what should be the actual velocity of the gas. Now, this will be is equal to that C0 into mixture velocity. Mixture velocity is the summation of superficial gas velocity and superficial liquid velocity. So, once you know that superficial gas velocity and liquid velocity and the gas hold up, you have to draw a graph based on your experimental data like this. Here USG plus USL, this will be in your x axis, that is simply Vm, and in the y axis you can have this Vg, that means your actual gas velocity, that will be simply here Vsg divided by epsilon g. Now, you will see whenever you are plotting this Vg versus Vm, you can get this data like this type of data you can expect. this type of profile you can expect from your experimental data. So, if you add this data here, you will see there will be a straight line. Now, if you extend this straight line, you will see there will be intercept of this straight line to this y axis. So, this intercept of this y axis will give you the Vd, that is called average drift velocity, whereas the slope of this line will give you the C0, that is distribution parameter. Now, this Vd and C0 you can get for different operating variables. If you know that increase the gas and liquid velocity, then you can get the different value of C0 and Vd. If you increase the viscosity, if you increase the density, if you add some surfactant there, you will see according to the physical properties variation, there will be a change of C0 and Vd. So, this C0 and Vd you can expect at different operating conditions. Now, to find out, to predict that C0 and Vd at different operating conditions, you know that several investigators, they have suggested several correlations for the C0 and Vd. So, C0 is generally actually 1.2, it is almost constant for upflow system as per Jouer and Findlay they have given, and drift velocity, it will be a function of that density of the fluid, and it is actually correlated by this equation. Whereas Jowett in 1981, they have obtained the C0 value, and they have suggested that, they have actually stated that this C0 will be a function of physical properties, that is as a function of density, and they have developed one correlations to calculate this C0 like this based on their experimental data. And Vd also, they have told that it will be a function of ratio of that gas to liquid velocity. So, that also they have suggested based on their experimental data, and they have given this equation to calculate that Vd. So, different investigators, they have developed different correlations for C0 and Vd. You can get that different value of C0 and Vd from this correlations. Whereas for downflow system, this Majumdar et al. In 2006, they have developed this correlation for this C0 and Vd based on their experimental data, and you can calculate this C0 and Vd from this correlations here. So, once you know that C0 and Vd based on your experimental operating conditions, then you can easily get what should be the C0, what should be the Vd, what should be the velocity distribution coefficient, and what should be the drift velocity. Once you know that velocity, then you can easily calculate what will be the average velocity. Now, without doing experiment, if you change the operating variables, accordingly you can get what should be the actual velocity inside the column. So, based on this drift flux model of Jouer and Findlay 1965, you can assess, you can analyze the that gas hold up from this equation. Next, another that important hydrodynamic characteristics, it is called mixing characteristics. So, in that case, what will be the degree of gas liquid mixing or gas liquid solid mixing there inside the column, that is very important, because this mixing characteristics will give you that what will be the performance of that particular mass transfer or heat transfer for the particular chemical engineering operation. So, in this case you have to estimate degree of mixing or intensity of the mixing by a certain method, and also what are the different variables that is affecting on the dispersion coefficient, and also what will be the model to analyze that axial dispersion there. Now, estimation of the axial dispersion coefficient of the liquid, you can estimate this mixing characteristics in gas liquid mixture in the downflow system by tracer techniques, by axial dispersion model. Now, in that case, based on that axial dispersion model, it is simply that how that profile of the concentration will happen in this case. Now, what is that C here? C is actually that concentration of the tracer. Suppose in your column, if you suppose insert some tracer like non-reacting chemical compounds, like air water system, if you add some sodium chloride solution like 10% of the total volume you supply, you will see with respect to time the concentration of that tracer particles will be changing inside the column, and that you can analyze just by taking that sample and analyzing its concentration of the tracer by instrument like conductivity meter or something. If you analyze that concentration, you will see that the change of concentration with respect to time, that will be a certain fashion like this. If you plot this concentration of tracer versus time, you can have this type of profile. Now, this profile can be predicted by certain model, just by stochastic model, but just from the basic material balance. That material balance will give you this ultimate that model equation. It is called axial dispersion model. Now, based on this axial dispersion model, what you are getting, that how this concentration will be changing with respect to time, and also parallelly if there is a flow, then according to that flow how this concentration will be changing axially, and this is your what is that diffusion of the concentration. So, based on this axial dispersion model, you can analyze what should be that dispersion coefficient, that is denoted by Ez here, and based on that gas liquid flow and at that particular operating conditions, if you feed this concentration profile, experimental concentration profile with respect to time, with this concentration profile by this axial dispersion model, you can easily calculate what will be the Ez. Otherwise, you can solve this equation to get that concentration profile and messing with that experimental data, then you can easily assess what should be the degree of mixing there. Now, solution of this axial dispersion model as per Levenspiel 1957 with open boundary condition, it is given like this, that is C theta is simply C by C0, what will be the initial condition of the concentration of the tracer, and C is the concentration at any time. So, C0 C by C0 will be C theta, and here this theta is called that dimensionless parameter of that time, that is T by Tm, Tm is called mean residence time, that is theta. So, theta will be equal to T by Tm, Tm is called mean residence time, that means how long that fluid will residing inside the column, and Peclet number, that is Pe, Pe is defined as here, that means U L by Ez. Here U means actual velocity of the liquid, L is the what is that length of the gas liquid mixture, and Ez is the dispersion coefficient. So, based on this solution of this axial dispersion model, and if you feed this solution with the experimental data of this C versus time, then you can get this parameter of that Peclet number and the Tm value. Now, how to solve this, how to feed this experimental data with this axial dispersion model, either by numerically or by some other method, that is called momentum method. Based on that moment method, you can get this solution of this method like this. Here from the first moment you can get the mean residence time, it will be defined as this here. If you know the concentration with respect to time, then you can calculate Tm from this equation, and then theta will be equal to T by Tm, and from the second moment of this equation you can have this variance of the distribution of this concentration from this equation based on this open boundary condition, and this sigma square, that is called variance, that you can calculate from your experimental data. Once you know that sigma square and Tm value, then you can easily calculate what will be the sigma theta square. This sigma theta square will be a function of Peclet number, that is Peclet number is simply defined as here, it is VSL Z by 1 minus epsilon g into Ez. VSL is the superficial liquid velocity, Z is the that means here axial length of that effective length of gas liquid mixture where the tracer is input and from where the sample of the tracer is collected, the length of these 2 points. And this Physical significance of this Peclet number is the transport by convection by transport by dispersion. If Peclet number is going to infinity, then you can say that plug flow, there will be uniform that flow, whereas if Peclet number is tends to 0, that means you can say that gas liquid mixing will be there, complete mixing. So, based on this you can get the degree of mixing in between based on your Peclet number data. Now, this is the way to find out that Peclet number. Once you know that Peclet number, you can assess it by dispersion number also. 1 by Peclet number, it is called dispersion number. If dispersion number is going to infinity, then you can say that more mixing. If dispersion number is going to 0, then you can say that plug flow phenomena will be there. Now, what are the different effects of these variables on this dispersion coefficient? So, you can say that if you increase the nozzle diameter, that means kinetic energy will be less, that means here jet velocity will be less kinetic energy distribution, in that case dispersion will be less. Whereas, if you increase the column diameter, you can say that there will be a mixing, more mixing inside the column, because the gas liquid mixer will get more circulation inside the bed and more residence time will be inside the bed. So, in that case you can get more mixing there and more dispersion there. If you increase the superficial liquid velocity, you can get more mixing, because their energy distribution will be high. Even if you increase the superficial gas velocity also, there will be a more dispersion of that liquid inside the bed, because there will be that internal circulation, even the random motion of the bubbles will disperse the fluid element there in more way. In that case, increase the gas velocity, increase the gas hold up, and if you increase the gas hold up, you can get that more liquid velocity inside the bed, more actual liquid velocity, and because of which you can get the more kinetic energy, more momentum transfer, more dispersion there. Now, you have to analyze these mixing characteristics by certain model. It is called velocity distribution model. Based on that velocity distribution model, what is the basis? The mixing of the liquid in the homogeneous system that will occur under the combined action of variation of the velocity and the motion of the gas bubbles in the liquid. So, this is actually based on the concept of Taylor that is given in 1953, that they told that this mixing will happens only under the action of variation of the velocity and the motion of the gas bubbles. Based on that concept, this velocity distribution model is developed to analyze the mixing characteristics. Now, according to the Ayres 1956, they told that this axial dispersion coefficient Ez will be a function of that axial velocity of the liquid as well as what is that column diameter. Now, if you functionalize this, then you can have this equation based on that Ayres, that will be equal to dc square b0 square by k dm plus dm. What is the dc? This the column diameter, b0 is the axial liquid velocity, and k is called that velocity distribution, that will give you form of velocity distribution, and dm is actually the molecular diffusion coefficient. In this case, if you are considering that bubble is moving, so here instead of dm you have to consider that bubble diffusion there, or bubble movement, bubble movement. So, bubble dispersion coefficient in that case you can get. So, we are defining in that way the dispersion coefficient due to the bubble motion, that is dB, is uniform in the column, and the contribution of the dB to the overall process is such in that case it will be much larger than that of molecular diffusion. So, according to that, we are just replacing that dm by dB here, and dB and k here depends on the operating variables, that geometry of the gas distributor here also, and V0 is the axial that velocity. In this downflow system, this will be equal to VL0 minus VLW, where VL0 is the liquid velocity, axial liquid velocity, and here LW is called the liquid velocity at the wall. Now, this VL0 will be equal to minus VLW according to the downflow system, and it will be equal to VL. So, ultimate V0 it will come as 2 into VL. So, this VL is the actual liquid velocity. So, this actual liquid velocity depending on the gas hold up. that gas hold up also depending on the superficial gas velocity, jet velocity, nozzle diameter, even column diameter. So, according to that we can get this correlations to find out that actual liquid velocity at the axis there. So, once you know that axial liquid velocity in the downflow system, if you substitute here and then draw a a graph here like this here, in this case dc square V0 square in the x axis, then we can define this way. If we consider that here this will be as x, and then we can write here Ez, that will be equal to x by k dB plus dB. So, if you plot this as Ez versus here x, then you can get this type of straight line there, whereas this intercept will give you the dB and slope will give you, you can get from this slope as 1 by k dB. So, once you know this slope and intercept, you can easily calculate what should be the k and dB. So, once you know this k and dB, then you can say what should be the velocity distribution and what would be the dispersion coefficient of bubble motion. So, if you know this dispersion coefficient of bubble motion, from which you can calculate, you can predict that what should be the axial dispersion coefficient of the liquid inside the column. So, this is the based on the bubble movement, how you can analyze the axial dispersion coefficient of the liquid inside the column. Next is another important hydrodynamic characteristic called bubble size determination, bubble size distribution. You can estimate this bubble size in the column whenever liquid jet is entering that bubble is the dispersed phase of bubbles and it will be moving downward. You can capture that bubble by a camera, high speed camera. Once you get this a snapshot of this bubble, you can analyze it by suitable image analysis software to find out the size of the bubbles, also shape of the bubbles. So, that is also important here. It is shown here in this picture that from this location we are collecting that bubble image by camera. After that it will be analyzed in the computer by a image analysis software. So, after getting this you can find out that interfacial area of each that bubble manually, that means or surface area of that bubble manually. Once you know that surface area, then you can say that pi d will be equal to surface area, that is perimeter. Once you know that perimeter or surface area or pi r square, then from which you can calculate what is the radius of that bubbles. Like this, if you know that more than 500 bubbles manually taking and then radius of that bubbles, average or mean radius of the bubbles or mean diameter of the bubbles, then if you segregate that bubble diameter in a bin in a class, then within a certain range of that bubble class you can have that distribution of the bubbles with its frequency. Like this here you will see that at different locations you will see that these are the bubble picture, and each bubbles you will see sometimes that will not be the uniform in size. Some bubbles will be elliptical, some bubbles will be elongated, some bubbles will be spherical. So, there are different shapes of the bubbles at different locations you will see, and in that case you have to consider the mean bubble size. And before going to that mean bubble size, you have to analyze individual bubbles whether it will be that spherical in shape or not. If it is not spherical in shape, you have to convert it to the equivalent spherical shape. If you are getting that elliptical bubble, you have to consider this elliptical bubble equivalent to the spherical bubble just by considering that equivalent bubble diameter and equal to the volume of that elliptical bubble. So, just by calculating that elliptical bubble here, in this case you the equivalent bubble diameter, how to calculate here by this equation. If you know the major axis and minor axis, that means maximum diameter and minimum diameter for that elliptical bubble, then you can easily calculate what should be the equivalent bubble diameter for individual. Once you know that equivalent bubble diameter for 500 bubbles or more than that, you can have the mean bubble diameter. That mean bubble diameter may be different type of mean. Souter mean bubble diameter in this regard, you have to remember the most acceptable or suitable bubble mean diameter there. It is called Souter mean bubble diameter. That Souter mean bubble diameter, it is defined like this here. This is called Souter mean bubble diameter. This is here, Ni is the nth number of bubbles and dBi is the individual bubble diameter. If you are considering number of bubbles 500, then accordingly you can get that dBs, that is volume to surface mean diameter, it is called Souter mean bubble diameter. So, once you know that Souter mean bubble diameter, and also based on that Souter mean bubble diameter, you can calculate what will be the number of bubbles are produced in that particular column at a particular operating conditions. That number of bubbles you can calculate based on this. It will be denoted by number flux, bubble number flux, it is gas volume metric flow rate divided by bubble volume into cross sectional area. So, you can define in this way, and finally you can calculate the bubble number flux based on this Souter mean bubble diameter. So, once you know this bubble number flux for that individual bubbles, you know that how many bubbles will be that this, how many bubbles will be within this range of bubble size, how many number of bubbles will be within this range of bubble size, how many number of bubbles will be within this bubble size range. Out of that total 500 bubbles, after knowing all those this bubble number flux, you can draw that profile based on that bubble number, bubble diameter with this bubble number flux. And if you know that total number, then bubble number flux divided by total number, you can get that bubble frequency there. So, bubble frequency versus bubble diameter, if you plot it, you will get this type of distribution. This is called bubble size distribution here at different locations. So, this bubble size distribution, this spreading of this bubble size distribution will be changing according to the operating conditions. If you are getting more spread, that means your bubble size range will be large, whereas if you are getting the narrow size distribution, that means here most of the bubbles will be within that very smaller size range. So, in that case you can assess what would be the bubble size distribution in that particular. Once you know that bubble size, that is Souter mean bubble diameter, you can obtain what would be the specific interfacial area, because this specific interfacial area is defined nothing but the total surface area divided by total volume of the system. So, it is called specific interfacial area. It depends on the gas hold up as well as the size of the bubble. So, once you know that gas hold up, that is epsilon g, and the bubble size, that is as a mean bubble diameter, that is dBs, you can calculate from this equation what should be the specific interfacial area. This specific interfacial area is very important for the mass transfer characteristics, because the overall mass transfer coefficient depending on this specific interfacial area, and mass transfer depends on that overall mass transfer coefficient. The mass transfer coefficient is a function of this specific interfacial area. So, you can assess what should be the mass transfer in the column between gas and liquid based on this interfacial area. And see here, this mass transfer happens based on this equation, and if you have that concentration of this compound transferring from one medium to the another medium, and how that mass transfer is happened, and this is the equation, and this coefficient is called the overall mass transfer coefficient. This overall mass transfer coefficient is nothing but a function of specific interfacial area. So, this specific interfacial area, once you know that, you can calculate overall mass transfer coefficient, and this overall mass transfer coefficient depending on the gas velocity inside the column. So, that for the downflow system you can easily predict what should be the mass transfer coefficient once you know that superficial gas velocity by this equation here. Again, you can calculate the heat transfer characteristics in this downflow system. That heat transfer coefficient you can calculate by this equation, that what will be the heat flux, and if you know that Ts and Tb here, what is that here H is called the heat transfer coefficient, Q is the heat supply rate, and this may be by that electric power or by other system, and I is called here ampere or current here, and V is called voltage, and A is called heat transfer area, and delta T, that is Ts minus Tb, the temperature difference between that heat sources, that is Ts and the bulk media Tb in the medium. So, once you know that Ts and Tb, then you can easily calculate what should be the heat transfer coefficient for your supply rate of heat in that case. And this heat transfer you know that can be calculated from this equation. If in this case if you are getting that non-linear distribution of the heat inside the column. So, overall and volumetric heat transfer coefficient, then you can calculate from this equation here. This will be your overall volumetric heat transfer coefficient. And here delta Tm is called that TLM, it is called logarithmic mean heat transfer coefficient. It is defined logarithmic mean heat transfer difference, that is temperature difference it is called. So, this can be obtained from this equation. And heat transfer coefficient, it is a function of Prandtl number. From this equation you can calculate what should be the Nusselt number, and from the Nusselt number you can easily calculate what would be the heat transfer coefficient. And this heat transfer coefficient actually depending on that Prandtl number, and also the how the mixing is happened inside the column. That intensity of the mixing, that is mixing coefficient, that is calculated based on this equation. And once you know that mixing coefficient, you can calculate what would be the energy dissipation in that downflow system by the liquid jet. And once you know that energy dissipation, you can easily calculate what should be that you know Nusselt number, that heat transfer coefficient based on this equation here. Because this Nusselt number, that is Hd by k, this is the Nusselt number is nothing but Hd by k, Hd by k. What is d here? D is called diameter of the column, H is called heat transfer coefficient, and k is the thermal conductivity of the fluid here. So, this Hd by k is a function of Prandtl number and also other physical properties of the system and energy dissipation. This energy dissipation you can calculate from the mixing coefficient there. So, heat transfer phenomena also you can obtain from this downflow system. So, for this you know hydrodynamic and you know transport processes like mass transfer and heat transfer coefficient, you can get more information from this my book here published in Elsevier. It is totally regarding the downflow system of this gas liquid system and also its application based on this mass transfer and heat transfer. It is given in more detail. You can go through this book for getting more information, even for better understanding of this system, for the process intensification of gas liquid system, for getting more interfacial area, more mass transfer, more heat transfer. Also you can follow other books, also other reference also journal papers also you can follow to get the more information. So, I think we have discussed more about that interfacial generation and how that intensification of the chemical engineering process based on the generation of the interfacial area in this module. So, we are actually going to finish this module for this you know interfacial area based process intensification. In the next lecture onward we will try to discuss something more about that process intensification process in the distillation system. So, thank you for this lecture.